into this equation, that would be false. What about Q30? 3 equal to 0 plus 3, that is right, therefore it is true. Okay. So we can apply this concept to the statement with a lot of terms, okay, or n tuple. Like we have x1, x2, x3 up to xn. Now we know the meaning of predicate. What is quantifier? Quantifier, the first definition. Universal quantifier of Px is the proposition Px is true for all values of x in the universe of discourse. Universe of discourse, okay, is like x, Px must be true for all the x, whatever x be. Okay, for example, we let Px is when x is less than 2, okay, the truth value of the quantification or x, Px, okay, and if we define the universe of discourse to be a set of real numbers, okay, means that x is a set of real numbers. Any real number, this must be true, right? Is that right? True or false? False, right? Because there are some, not all of the x would meet this statement, right? There are some x that is greater than 2. Must be less than 2. That's not true. Not right. Okay. So that's the concept of universal quantification. Next one, existential quantification. Existent means that there must be some that exists an element x in the universe of discourse such that it makes Px true. Okay, at least one x such that Px is true. What about if we have Px x greater than 3? If the universe of discourse is a set of real numbers, is it true or false? Is there any x that make this to be true? Yes, right? X greater than 3. How about when x is equal to x plus 1? Is there existing anything? No, there is none. Therefore, it is false. Okay. Now, if we have combination of both universal quantification and existential quantification, just like this, we can find out the truth value of the statement, right? Like for all x, all y, x plus y equal to y plus x. Is that right? Yes, right. According to what law? Commutative law, right? X plus y equal to y plus x. for all x, there are some y or existing some y such that x plus y equal to 0. Is that correct? Right. When x is a set of real numbers. That's true. Right? Real numbers. But if x is a set of integer, is that still true? Positive integer. False. Right? So it's also depending on the context of the set, the universal of discourse. Okay. The last one is when all of the x, all y, and all z, we can find out if this is true or not. It is true because of the associative law. When x, y, and z are set of real numbers. Okay. If we have x positive integer, y negative integer, or something like that, if we x, y, and z are like belong to different sets, different types, we have to check one by one, right? Each of them, if this statement is still true or not. Okay, so far we have covered 3 sections, right? 1.1, 0.2, and 0.3. Okay, we are not going to cover 1.4. Okay, 1.5 would be discussed next week, not today. Okay, now we are going to jump to 1.6 first. Set. First definition. Set is an unordered collection of objects, right? I think all of us know, we have learned before about the set. So just briefly overview of what it is, and then we will move on. Okay. So the object in a set is called elements, okay, or members of the set. Example, the set of all vowels in English alphabet would contain 5 elements or 5 members, A, E, I, O, and U, right? We define that 2 sets are equal if and only if they have exactly the same elements. For example, this set, is this right? Are these 2 sets equivalent? No, 4 is missing. Right? 1, 3, 4, 5, 7. So this set must have 5 elements at least. Okay. If we have multiple identical elements, we just count it as 1. So this set, each of these has 5 elements, not 7. Let's see Venn diagram. This is the universal of the set. Okay, we use U stand for universal set. Empty set or null string, we use the symbol, this symbol, or like this, a set with no member, no element, right? How about subset? We use this symbol if all the x, okay, when x is the member or elements in set